Hi everyone, my name is Qian Zhou. I'm a PhD student in the Human Communication Lab in ECE department under the supervision of Professor Sidney Fields. And today I'm here to introduce our work on the interactive Spherical Fish Tank VR. And so Fish Tank VR is a type of VR that first be presented by Colin Ware in 1993. And it can provide perspective-corrected imageries on high-resolution displays. And the previous literature has found that Fish Tank VR can provide better task performance on those cognitive tasks that specifically require those careful examinations. And one of the problems of the Fish Tank VR is it only supports limited viewing angle due to its stationary 2D display. So this sort of constraint on the head of movement that user can have with respect to the display. So to overcome this limitation, we designed a Spherical Fish Tank VR that supports perspective-corrected imageries from all angles. So because this is like a perspective uncorrected display and on the spherical screen. So we use a projector to generate those images. And instead of using one projector, we use multiple projectors that are rear-projecting through a projection hole at the bottom of the sphere. And this is to create a scalable and high-quality display. And with head tracking, this become a view-dependent imageries that allow walk-around visualizations so that user can look into the display. And so while interacting, this spherical display supports various forms of natural interactions on the surface of display. And while interacting, the spherical screen itself becomes a special reference that connects the virtual world to the real world. One of the challenges that we have when building the Spherical Fish Tank VR is sort of how to make sure that those projectors can work together to generate a seamless display. And so to generate a seamless display, we will need an accurate calibration approach of all those to calibrate all those multi-projector display so that we know each projector where they're projecting on. And we can stitch and blend those multiple projections to create a seamless display. And we develop, and failure to do so will cause those artifacts that can easily break the 3D illusion. And to solve this problem, we developed an automatic calibration approach by putting a camera at the bottom of the sphere and project those blob patterns onto those spherical display and have the camera observe that, and then we reconstruct those projected patterns. We will repeat this process for each projector and use all those reconstructed 3D pattern to recover the 3D coordinates of each pixel on the display. So the result is a calibrated surface that has sub-millimeter on-surface error to represent like a seamless display. Once we have the calibration data, we then import this calibration data into a two-pass rendering approach in Unity. And this coupled with head tracking, user can move around the display and so that the corresponding pixel will light up based on the user's viewpoint. And this is how basically like the technical part about how we build this kind of unusual display. And once we have the display working, we started to look at the interactive content that sort of can benefit from this unusual display. So this brings us to the second part of this presentation, which is our work in progress on the 3D interactions. So as we all know, like working in virtual environment isn't very easy. Although we conduct the 3D task every day, like very frequently, it is still challenging to leverage our daily skill into the virtual environment. And the reason behind it are very complicated, but one perspective is look at like what kind of feedback we can get when we interact with the real environment. So basically, for example, when we're playing with the Lego pieces, while we get visual feedback, we get haptic feedback, and sometimes we get auditory feedback to help us conduct the 3D task. However, in the virtual environment, we can only get a very limited collection of this feedback. And even within those collections, those 3D cues can conflict with each other, and this causes those famous problems like the vergence accommodation conflicts in those VR headsets. So basically, this kind of limitation becomes a problem when we're trying to interact with in 3D in virtual environment. But fortunately, previous research has found that the way people use those 3D cues greatly depends on the purpose of perceiving. In other words, depends on the task that we're doing in 3D. So this stands for the reason that if we can say understand and identify those critical 3D cues that are significant to a specific task, even if some of the depth cues are missing, the user may still be able to interact in 3D easily as long as we provide those critical 3D information to them. And so basically, this kind of assumption is related to one of our research goals here, is to identify those tasks that can be benefit from the 3D cues provided by our Spehrical Fish Tank VR. And this, coupled with appropriate designed interaction techniques, can make the 3D interaction easier. So to perceive, this is a large goal, and so to perceive this goal, we've tried a lot of explorations, different kinds of interaction with the Spehrical Fish Tank VR, including stylus, controllers, touch, and the mobile device. So for stylus, one of the demo we built with the stylus is we used the stylus as a handheld flashlight that sort of throw a light into the scene so that user can use that light to interact with the content inside while also moving around. So we present this demo and at the conference of IEEE VR last year. And participants are actually they accept this metaphor quite well. So that what we observe is they can naturally move around the display with it while at the same time interacting with the object inside. And here is another demo we built, but with controllers. And we have the user can use the controller to control a virtual drone to pick up the apple in a 3D target acquisition task. And user will need to get the depth right in order to get the apple and in order to resolve the occlusions by moving around the display. We presented this last year in the Kai interactivity. But then the thing that we found is lots of users, when interacting, they stand still, even if the target, for example, drone is occluded by something. So in this case, the head movement is not naturally triggered. And further, we found that for those users who basically had previous experience in virtual environment, for example, they play a lot of 3D games, this becomes easier. So the thing that we observe is they can controlling while at the same time moving around their movement. So this suggests combining those existing input controllers with the head movement simultaneously is probably not always a natural skill and requires some sort of training, but this also depends on the task. So following those kind of findings, we conducted a pilot user study using touch. So we built a touch interface with the spherical display by putting an infrared source under the sphere and use a camera to capture those touch information. And this study we did is we have the user to touch, to rotate the cubic stimuli and decide whether the layout of the feature of the inner cube can be matched to the features on the skeleton cube. However, the thing we found for those users is users who managed to learn as how to combine those two kind of input at the same time managed to improve their task performance. However, it seems as learning to like combine those two kinds of inputs is not natural and requires a lot of training actually in our experimental setup. So those things like those findings basically suggest like perhaps like sort of connecting those multi-degree of freedom from your hand, from your camera and other things is probably require more research to look at the eye-hand coordinations. So that will be probably our next step to go. And for all those explorations, it turns out like finding the appropriate visual stimuli and interactive content that can be a good fit to this sphere is a challenging task that we're currently working on. And we believe that our effort on exploiting those the unique feature of this unusual display can help us understand the difficulty of 3D interactions. And beside those single-person interaction, we also worked on the multi-person co-located experience with the Spehrical Fish Tank VR. We developed two different methods to support multi-view at the same time. One is to use shutter glass. We synchronize the shutter glass with the content inside in time domain. And the other one is we use a second screen that has been tracked, looks like a window to interact with the content inside in the same 3D world. And for the shutter glasses, we still project both of the U on the surface of the sphere, but by synchronizing the content or with the shutter glasses, each person can only see their own view. So this can support, like make people can work and play together, co-located at the same time, and they can point and select into the same object in the scene. Then for mobile screen, more people can be co-located in the same scene using a mobile screen. And the mobile screen has been tracked so that it looks like a window that looks into the 3D scene so that people can move around with the portable screen and interact with the content inside. And they can collaborate it by pointing to the same stuff and collaborate it with the other user using the spherical screen. So, so to wrap up, like we've presented our most recent work on the Spehrical Fish Tank VR, including approach, calibration, and some of our findings regarding the work in progress on 3D interaction and multi-person experience. In the future, we'll work more on the 3D interactions and the multi-person support. And so thank you.